All right, so today we're going to look at the binomial probability distribution. And this one is very important, very closely related to the sample proportion. And it does all kinds of, I mean, there's so many different applications where this is applied. And so I will basically introduce the binomial distribution, and then we'll look at several probabilities and applications. Here, we are going to use there is a very, very messy mathematical formula, and we're not going to use that formula, but rather we're going to use a function on the calculator. So today, for the first time, you're going to be introduced to one of the distributions. It's above the vars, and it says DISTR. And the normal distribution is in there, but so is the binomial. And so we're going to be looking at binomial probability calculations. Now, the big difference between what we did in section 6.1 and what we're going to be doing today, the binomial distribution is a discrete probability distribution. So all of the formulas that we just used to calculate the expected value in section 6.1 can be used to do the problems in section 6.2. But there are simpler formulas that we can use to calculate the expected value in this setting. And so I'll introduce you to those. Now, you can think of the binomial distribution as being kind of a special case of a discrete probability distribution. And so it has specific formulas and so on that go with it. But generally, in this section, we're going to calculate the mean, which is the expected value, and there are different variables that it uses. The mu sub x, sometimes they use the expected value. So we're going to be calculating the same thing. It just that it comes with a simpler formula. We're also going to be calculating the standard deviation. And again, that comes with its own formula. The big difference between the previous section and this section is that we're going to be calculating probabilities. The probability that x equals, some number like 3. We're going to be calculating those probabilities with a formula as opposed to having been given those probabilities in a table. So the probabilities will not be given to you. You have to calculate them using this special binomial probability formula. Okay, so that's kind of an overview. So you're going to see a lot of similar things today from what we did last time, but we're in a very, very narrow situation. The good news is that this narrow situation applies a lot. Okay, in order to use the things from this section, you have to recognize that you're in a binomial setting. And for a binomial setting, they say you're in a binomial experiment if the following things occur. The experiment is performed on a fixed number of times, and the fixed number of times is equal to n. N is the number of trials. And I believe on your calculator, when you actually enter this in the menu system, it's going to say, what are the number of trials? That's the n. You have to be able to identify that number. The trials are independent. Think about selecting a sample of 1,000 from a population of 100,000. Basically, the individuals are independent of one another, or however they respond to a survey or whatever. Another example is you can think of the coin example, flipping coins. If you wanted to count up the number of heads, for example. Each trial, each coin toss is independent of the previous one. If you get 6 heads in a row, the probability of getting a head on the next one is still 1/2. Earlier results do not influence later results. For each trial, there are 2 mutually exclusive disjoint outcomes, and that's where the bi comes in binomial. And we're going to define successes or failures. And the value of x, which is the number of successes, whatever that means, it's going to mean different things in different contexts. For example, if you're flipping a coin 7 times, the number of trials would be 7, and the number of successes can take any value from 0 up to that maximum number, 7 in my example, or n in general. So you need to be able to, the values of x will directly fall or be calculated based on the trials. So the value of x will always begin at 0 and go up by 1 up until you reach the number of trials. It's the number of successes. It would be like this. If you flip 7 coins and you wanted to count the number of heads, well, if you threw 7 coins down, the number of heads that would appear would be 0 or 1 or 2 or 3 all the way up to 7. But you couldn't have more than 7 heads appear. So that's why we stop it at 7. And then the probability of a success is little p, and you have to be able to identify that number. In the coins example, the probability of a success on 1 trial would be 1/2. That would be the probability of getting ahead. If you can identify the n and you can identify the p, then you know that there are 2 outcomes, or the experiment can be changed so that it does have 2 outcomes. And by that I mean this: if you roll a die, we generally think that there's going to be 6 outcomes, 1, 2, 3, 4, 5, 6. However, if you define the experiment in the following way, you either roll a 3 or you don't roll a 3. Then you do roll a 3, don't roll a 3. Those are 2 outcomes, and they're complements of one another. So even in situations where there are multiple possible responses, we can convert it to just 2 responses, a success and a failure. The other thing is that once you're going to see Q in the formula, and the Q is 1 minus P. So if P is the probability of a success, then Q is the probability of a failure. And I'll put failure in quotes too, because it's not really a failure. In the coin example, a failure would be getting a tail. It's just kind of not the outcome that you were looking for, that you wanted to count. And sometimes they call that just 1 minus P. Okay, so the first set of problems is just to determine if you're in a binomial setting. So look for this. Can you identify n? And you can identify p. And there are 2 outcomes. So really these 3 things are what's important. 2 outcomes, you can identify n, and you can identify p. If those 3 things occur, then you're probably in a binomial setting. So let's take a look at these. There's just a bunch of them. And notice that all you're asked to do here is to determine, is it a binomial experiment or not? So can you identify n, and can you identify p, and are there 2 outcomes? So let's take a look at number 8. A random sample of 30 cars in a used car lot is obtained, and their mileage is recorded. Now, car number 1 had 100,000 miles on it. Car number 2 had 20,000 miles on it. Car number 3 had 330,000 miles on it. Is this a binomial setting? Okay, so, and the reason that it's no, and because we have to be able to identify, we can select n. We do know that n is equal to 30, but we don't know what the probability is there. It's a probability of a success. So if you think of the other thing that fails is that there are more than just 2 outcomes, because a car can have 100,000 miles or 200,000 miles or 150 or 30, can have all kinds of numbers. There's not just 2 possible outcomes. So we would say that this one is not in the binomial setting. Let's take a look at number 10. A poll, and when you're identifying the n, if you're doing it in an empirical setting, the n will be the sample size. So up here, n is the sample size. Okay, so we don't have the value of p here, but it is something. And because there are two outcomes, they either believe Congress should reform Social Security or they believe Congress should not reform Social Security. So there are two outcomes, and the probability is not given, but if it was given, then this would be a binomial setting. And I think probably they will answer yes on this one, because while they don't give us the probability, we do know that a certain percentage will respond yes, that Congress should reform Social Security. Okay, why don't you take a look and do 12 through 14 there. And just yes it is or no it isn't. And this is the first step that we have to do. If we know we're in the binomial setting, then we can apply all the formulas of this section to the problem. And so it's important to know. So if you'd like, just go ahead and put into the chat the number and yes or no. Yes, binomial, no, not binomial. Number 12, yes, binomial, no, not binomial. Okay, looks like we have a lot of yeses. All right, so the number of trials would be 3 because we're selecting each time. The probability of a king would be 4 out of 52, and that's the same every single time. And the number of kings is recorded. So X would be 0, 1, 2, or 3. If you're only drawing from the deck 3 times, the most number of kings you can have would be 3. So X is the number of kings. And while there are many, many, many possible cards that you can get, you can think of this experiment as being, I get a king or I don't get a king. So there are 2 outcomes. And so I agree with you. Yes. What about 13? Well, I'm seeing a lot of no's on this one. A basketball player who makes 80%. So basically they're giving you the value of P there. And Q would be 1 minus P. I just want to give you another example of that. So P and Q must add up to 1. So if the probability of making a free throw is 80%, then the probability of not making the free throw would be 20%. And this one kind of is more linked to success and failure than many of our other examples. Shoots free throws until she misses. Okay, so N is unknown. And because N is unknown, it just says you just continue to shoot. Another problem could be that the basketball player shoots 10 free throws. If we knew that what the value of N was, 10, in my example, then we could say maybe it's a binomial probability. But since N is unknown, we would say, right, no. And number 14, I see some yeses after that. I'm not sure if those are 13 or 14. Who reaches base safely 30% of the time. So that would be like well, it's not quite a batting average, but usually for batting averages, they would write it as a decimal rounded to 3 decimal places. So if it's not quite reached base safely, because you can get a walk that doesn't influence your batting average, but let's assume that this is it. So this would be the p-value, the probability of successfully reaching base. So Q would be equal to 0.70. And then we would need to identify the X, all right? So, so bat until he reaches base safely for the 3rd time. The number of at-bats is recorded. Okay, so again, we don't know how many times this batter is going to bat. And for the same reason in number 13, since we can't identify N is not given to us at the beginning, then this one is not. All right, so determining whether a given setting is binomial is the first step. Now, most of the problems that you have after this point will be binomial. And so, again, remember what we're going to do. We now know what the setting is. Our goal is to calculate probabilities. In our previous section, those probabilities were given to us, itemized, listed in a table. So we didn't have to do any calculation. We just had to go interpret a table in order to calculate some probabilities. We're also looking for the mean and the standard deviation. So just like in our previous section, we were calculating mean, standard deviation, and several probabilities. We're going to do the same thing today. It's just in a different setting, the formulas are slightly different. And so I wanted to give you this formula here. This one right here is n choose x. It's a mathematical formula that identifies a way to count the number of possible outcomes or possible configurations. We call them combinations. And if you want to see this function in your calculator, if you want to play around with it, it's in the math menu. You hit the math menu, and then you go over to the probability menu over here. You'll see it right there, NCR. And that's the math menu, and then the probability submenu, and then it looks like it's option 3. P is our probability of success. X is the probability that we're trying to calculate. And then you can see X goes from 0 up to N, where P is the probability of the success. So they're defining the P and the X and the N in the same way that we defined it earlier. Okay. We don't want to use that formula. Instead, you're going to use the TI to calculate probabilities. All right, so the 3 things we want to do: probabilities, mean, and standard deviation. The mean and standard deviation we'll get to later. Right now, we're looking at how do we calculate probabilities. Here's the mathematical formula. I X'd it out because I would prefer, well, you can do the way you want to do it, but it's so much easier with the calculator, and I want to show you that. The probability that X equals 3, let's say N is equal to 5 and P is equal to 1/3. So Q would be 2/3. 1 minus 1/3. The probability that X is equal to 3, with this information, if you were going to use this formula up here, it would be 5, choose 3. That's the NCR version. And then you got to multiply it by P to the X power, and then times Q to the N minus X, which is 3. So you can see what a kind of a mess this would be to try to calculate it with your calculator. But what we're going to use instead is this function called binomial, and then, well, we're going to use PDF. And this is a probability distribution function, or probability density function, EF. It helps us calculate probabilities like this. The order in which you enter things in will be N, and if you do the menu, this is the number of trials. And then you write the P, which is the probability, and then you write the X. In our case, since X is equal to 3, we would put 3 in there for X. And I'm not sure if they just say this is value or what they say in the menu. We'll look at it. All right, so that is the function, the binomial function. You can find, let me get it over here. It's in the distribution menu, so right above vars. So you have to hit second vars, and together those get you the distribution menu. And then you'll notice that nothing that looks like binomials on the first page, but there's an arrow going down, the number 7. So if you scroll down, you'll see two binomial functions. I'll talk about CDF next, but the first one is PDF, and that's the one you want. So it's option A, and binomial PDF. So that's where you find it. And you're going to be calculating binomials using these phrases here: fewer than, no more than, at least. So it tells you which math inequality symbol to use here for these different phrases. So this is just more of a reminder than anything else. All right, now let's take a look at some examples. They give us the three things that we need: the n, the p, and the x. And notice here it's x equals a specific number. And then down here you have the inequality symbols. So for these up here, we're going to use binomial PDF. And this is when you have one specific value. And if you have an inequality symbol like this, we're going to use binomial CDF. C stands for cumulation, accumulating. You're going to add up a bunch of probabilities from 0 up to some ending amount. Okay, so use binomial PDF for one specific x value, and use binomial CDF with inequalities, which would suggest presumably multiple x values. All right, let's take a look at maybe one or two here. 18. Maybe I'll do one, I'll ask you to do one, and then we'll do some inequalities as well. Okay, so n is equal to 15, and p is equal to 0.85, and they give you x is equal to 12. If they ever ask what q is 1 minus p, so you're going to subtract 1 minus 0.85 here. And this is the probability of a failure. Symbolically, they want us to calculate the probability that x is equal to 12. Here's our x value. Sometimes they'll just write it this way: the probability of 12. All right, binomial PDF, because this is one specific x value. We have to enter in the n first, and then the p, and then the x value. And remember, these are binomial, these are probabilities, and so they have to be numbers between 0 and 1. So I'm going to select option A, and then 15. If you get the menu where it says the number of trials, you're going to put 15. For me, I just enter it all in. I need to know, I know that n comes first, and then p, 0.85. So then you would say the probability, the PROB, is 0.15. And then they're going to give you the x. Do they say value there, or what do they say in your menu? Does it say trials? Okay, I need some confirmation here before we go on.
Here's trials, a p, and x value.
Okay, so trials is 15. It just says p?
Yep, just p.
Not probability, okay. And then the x, it just says x value here?
Yes.
Okay, x value, 12. All right, and we're looking for a number between 0 and 1. This is the probability that if we have 15 trials with an 85% probability of getting a success on every individual trial, what's the probability that you would have exactly 12? And there it is. 0.218. And you can convert that to a probability, if you, or a percentage if you like, to interpret it as well. So that's it for that one. All right, let's take a look at an inequality here. You know, some of the fancier calculators now allow you to establish the initial, the smallest x value, and then the largest one. But with this calculator, it only calculates, it's going to ask for the same 3 numbers, but it's going to calculate the probability that x is less than, or could be less than or equal to. Okay, now let's go less than or equal to. Then you would put n and p and k. So this accumulates. So this is equivalent to the probability that x equals 0, plus the probability that x equals 1, plus the probability that x equals 2, plus dot, 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 plus the probability that x equals that last number k. So it adds up, it accumulates probabilities beginning at 0 and ending at this last number k, whatever that is. So let me do problem, let's see, number 23. You have n equals 9, and p is equal to 0.2, making q equal 0.8. These two have to add up to 1. And you have x less than or equal to 3. All right, now symbolically, it would look like this. The probability that x is less than or equal to 3. The function we would use is binomial CDF. PDF uses just a single x value, is calculating the probability at a single x value. CDF accumulates probabilities from 0 up to the ending amount of 3 in this case. We're going to enter in 9 and then 0.2, and then we're going to end at 3. And what this really means is the probability that x equals 0 plus the probability that x is equal to 1 plus the probability that x is equal to 2, and then finally plus the probability that x is equal to 3. It adds up a sum of a bunch of probabilities at individual values. And since this is a discrete probability distribution, we're not going to have any x values between 0 and 1 or between 0 or 1 and 2 and so on. So less than or equal to 3 means here in a discrete setting 0, 1, 2, and 3. All right, so you can calculate that with the calculator. I want to do the table now. This is number 23, where we have n is equal to 9. Most of the time you're not going to do the table, but it's helpful to understand what you're doing if you do this table. P equals 0.2. Q is equal to 0.8. Is that what we have? 0.2, 0.8, yep. And then x takes on values between 0 and goes all the way up to the value of n, which is 9. In section 6.1, they gave you tables like this, or at least they gave you the information that would enable you to find the tables like this. So we're going to put all the numbers of x, possible values of x from 0 to 9 in our table. Then each one, if you wanted to calculate the probability at 0, n would be 9, p would be 0.2, and then you would plug in the value of 0. If you wanted to calculate the probability at 1, you would use binomial PDF again. PDF is the calculator function that we use to calculate the probability at a binomial probability at a single x value. And you would just continue in this method all the way down, 9, 0.2, and 2. This one down here would be binomial PDF 9, 0.2, and 9, and so on. Let me do just one more. Binomial PDF 9, 0.2, and 3. The idea? So you can generate this whole table using the binomial PDF. Now here's how you would do it on the calculator. I'm going to use list commands. I think we've used these in the past. I'm going to clear out my lists, and I'm going to enter in the x values into L1. And then I'm going to put the probabilities into L2. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You want all those numbers in L1. Now, instead of typing out all this stuff, really the binomial PDF is the same function that we're using over and over again. The 9 is the number that we're putting in for the n. The 0.2 is the number that we're putting in for the p. And the only thing changing is this last number. Well, that last number is precisely the number that appears in L1. So we're going to enter a formula to do that. Highlight L2. And then go find binomial PDF. It's in the distribution menu. If you scroll down, you'll see it, binomial PDF. That goes to your input row. We have to specify the number of trials, n, 9. And if you go to the menu, then just go ahead and type in number of trials is 9, p-value, probability value is 0.2. What's going to change here is that the number I want to put here is not one specific x value, but it's the value that appears over here in L1. So I'm going to hit second and then the number of 1 so that that last number is L1. Now when I hit enter, it gives me all the probabilities from 0 down to 9 in a nice table. So I'm going to write these down. It's kind of hard to see, but this is 0.13422. This is 0.30199. This is 0.30 also 19. Same thing. 0.17616 and so on. 0.06606, 0.101652, 0.00275, and then I've got to scroll down. Okay, so 7 is 1, 2, 3, okay, and 8 is that's E negative 5. 1, 2, 3, 4, 1, 8, 4, 3, and 9 is even smaller than that. 0.1, 2, 3, 4, 5, 6, 5, 1, 2, something like that. It's a very, very small number. Now, if I add up these 4 probabilities here, I'll just do that on my home screen. 0.13422 plus 0.30199 plus 0.30199 plus 0.17616. I get this number here, 0.91436. And that's rounded. But you'll notice from your calculation back here that when you evaluate binomial CDF 9.2 and 3, you will get that same sum, 0.91436. So let's check it out. We're going to go to the distribution menu, binomial CDF, n, number of trials is 9. The probability for each trial is 0.2, p-value, and then the x value would be ending at 3. And so I'm going to hit enter, and you can compare it to this number here. And so you can see that this number rounded would give you this number here. All right, so the added difficulty in this section is that you have to calculate the probabilities yourself. And you do it with this probability formula from the TI-84. It's not too bad, but you have to know the difference between PDF and binomial PDF and binomial CDF. All right, now that we know how to calculate probabilities, we're going to move on, and we're going to calculate mean and standard deviation. Now, the mean is still the expected value, and then the standard deviation. But when we identify in a binomial distribution what the value of n and p are, the mean is just you take the n value and multiply by the p value. Let me give you an example. I don't want you to calculate anything. Just write in the chat what you think the answer is to this question. If you flip 6 coins in a row, maybe you have 6 coins in your head and you just throw them up in the air and they come down. And let's say that our x is the number of heads that appears. If you throw 6 coins in the air, what do you think the average number of heads that would appear if you threw 6 in the long run? If you did this 100 million times and you just recorded the number of heads, sometimes you'd have 0 heads. That would be unusual. Sometimes 1 head, sometimes 2 heads, sometimes 3 heads, all the way up to 6 heads you could possibly get. But if I asked you just this question and I wanted a number answer, put your number in the chat. How many coins, if you flipped 6, how many heads do you think would appear? Just use your intuition, no calculation. I'll wait. Here's the question again. If you flip a coin, flip 6 coins, how many heads do you think would appear? What do you expect to appear? How many heads? -4. Oh, approximately 4. 3 or 4. Okay, yeah, so looks like 6 of you are responded. And I think the most popular answer is 3. But here it is. All of these things kind of mean the same in this context. And we know now that this is n times p. Here's the formula. N times p. So if you flip 6 coins and you're counting the number of heads, and the probability of getting a head on any one toss is 1/2, then you would just take the 6 and multiply it by 1/2 and get 3. So yeah, your intuition for most of you was correct, and that is if you flip 6 coins, you would expect to see 3 heads. Kind of makes sense in this case. But that's the mean. I will point you to a simpler standard deviation calculation there. So remember, these same 2 formulas that we saw in the previous section, they also apply. So if you wanted to, you could just sum up, each outcome times its corresponding probability. And you would get the expected value that way. And over here, if you summed up, well, we're going to take each data value, subtract it from the mean, square that, and then multiply it by the corresponding probability. And then at some point, we're going to want to take the square root of that. Very messy formula. This one is much nicer. Okay, so you can calculate, or you can present the probability distribution in a graph and a table. What you'll find is if this is true, I just say n times p times q larger than or equal to 10. If that's the case, then the binomial distribution will be approximately bell-shaped. If it's n times p times q is less than 10, less than 10, then what you're going to see is you're going to see a, if p is less than 0.5 and this thing holds, you're going to see a skewed right distribution. And if p is greater than 0.5, you're going to see a skewed left distribution. If npq is less than 10. Otherwise, if npq is greater than 10, then you're going to have a bell-shaped distribution. Okay, let's take a look at a problem like number 30. They ask you to, what do? Construct a binomial probability distribution with the given parameters. Okay, so n is equal to 8, and p is equal to 0.5, and so therefore q is equal to also 0.5. If you're going to calculate the mean and the standard deviation, notice you need n and p. This one you can have n times p times q, because 1 minus p is q. So I'll be using q a lot instead of 1 minus p. But first thing we'll calculate is the mean. And I'm just going to remind you that this is the expected value. And it's a much nicer formula. You don't have to enter things into lists. You can just take n times p. In this case, take 8 times 0.5, and you get 4. So the mean is 4. Very simple formula. The standard deviation is the square root of n times p times q. Just take those numbers that you now know, 8 times 0.5 times another 0.5. And that one's 4, half of that is 2, square root of 2 is 1.414. All right, they tell us to calculate these same 2 numbers using the section 6.1. So if you did that, then since n is equal to 8, then our x values have to go from 0 to 8. And then I have to calculate the probability that x is equal to 0, the probability that x is equal to 1 and 2 and so on. We've done this before, but I'm just going to do it again. Highlight L2, go to the distribution, select Binomial PDF, and we're going to take 8 and 0.5, and then whatever number is in L1. Oops, L1. And there are all the probabilities. So you first need to generate the table, and then once you do that, we're going to calculate with one variable statistics. The X list is L1, the frequency list is L2. We calculate, and notice what X bar is. Notice what SX is, or sigma X, the mean, and the standard deviation that we just calculated. Let's see if I can get them both on the screen here. We calculated the mean to be 4, there it is, and we calculated the standard deviation to be 1.414, and there it is. So the point here of this problem is that you can use the techniques of section 6.1, the same thing that we did in those previous problems, to calculate the mean and the standard deviation. But it's much simpler to calculate these with these formulas. Since I have the data in L1, I might as well just, I'm not going to do a histogram because a histogram is requires all the data to be known. We'll just do a scatter plot. We can kind of see the shape if we do a scatter plot. There it is. Pretty bell-shaped looking. So if we were to draw a graph, it would look like this. High in the middle and then kind of coming out this way. Bell-shaped. This would be the scatter plot that corresponds to it. If you just kind of connect these points here, you would have this graph. So it's not a histogram, but it gives us what we want, the shape. The other place where you can see that is here. Notice how the probabilities at the extremes are small, and then they get larger until you get right here in the middle, where it's the highest probability. Then they drift off back to the smaller numbers. So it's highest in the middle, and then drifts off on the sides. Bell-shaped. Whenever p is equal to 0.5, you're going to have a bell-shaped binomial distribution. Let's check this up here. If we take, well, n is equal to 8. Now, this one's going to be bell-shaped, but it doesn't satisfy this. So maybe I'll just say, or if p equals 0.5. The further you get away from 0.5, then you really need a very large n value to make it look bell-shaped. Okay, so the next few problems are all applications. So these applications will be much easier in your homework, or at least when you figure out how to do them, than when you see them all together with just a bunch of other problems. The hardest part here is to try to figure out if this is binomial. And since you know these problems are in this section, you'll know that they're binomial. So let's take a look at how we would answer this application here. This is on morality. In a recent poll, the Gallup organization found that 45% of adult Americans believe that the overall state of moral values in the US is poor. Okay, so this here, in empirical studies like this, when they give you a percent, that's going to translate into the probability value, and we're going to convert that percent into a decimal. And since 45% of the entire population think that we have a lack of moral values, then we're going to say this: if we randomly select from the general population, the probability or the likelihood that each individual person selected would say, yeah, we have moral issues in this country, would be 0.45%. So we're going to assume that this is an independent selection because there's so many Americans. Suppose a survey of a random sample of n. Now n in empirical setting is going to be the sample size. And so generally the percent in these problems will be the probability, and the sample size will be the number of trials. And in a question like this, well, when you ask some Americans if you think that the overall state of moral values is poor, then you would be treated as a success. So you either think that the moral values are poor or you think that they're not. So there are two outcomes. So this is a binomial setting. So let's answer the questions. The other preliminary thing that you'd want to do is maybe to calculate Q. And that's 1 minus P. So 1 minus 0.45, which would be 0.55. All right, let's take a look at the problems. A, says find and interpret the probability. So we're looking for a probability here that exactly 15 of those surveyed feel the state of morals is poor. All right, so that's a success. So what's the probability that X is equal to 15? Because they're asking for the probability of one specific X value, so out of the 25, 15 will say, exactly 15, and that's it. Then it's a probability, so we're going to use this notation, and we're going to use Binomialpdf. And we're going to use the PDF version of this function because it's at a single X value 15. It's not less than or equal to 15 or greater than 15. It's exactly equal to that one value. So we're going to put the number of trials, N first, 25. That's our sample size. We're going to put the p-value next. That's the probability. And that's going to correspond to that percentage that they gave us at the beginning, that 45% think that the state of moral values is poor in this country. And then the last number corresponds to the probability. That's your X value. And since we're looking at X equals 15, that's the number that goes there. For PDF, it always goes there. For CDF, it's going to change slightly. Okay, so this is a calculator exercise. Okay, go to the distribution menu and scroll down till you find Binomialpdf. And then we're going to enter n, number of trials, 0.45, the probability, p-value of a success, and then 15. And there it is, 0.052. And, you know, the interpreting probability part is not different than what we did in the past, because it does say find and interpret. And we interpret these probabilities as percentages. So 5.2% of the time, 15 out of 25 respondents to a poll will say the state of morality is poor. And you can just go into more detail, you know, in the US. So most of the writing involves just defining what the probability is. All right, so they're always going to give you one, or they're usually going to give you where you calculate the probability at one specific value. All right, now let's go to part B, where they're going to ask you to accumulate probabilities. And so then I'll try to give you a general strategy on how to figure these out. So get this up here. B, find and interpret the probability that no more than. Okay, so no more than. We want to translate that into our mathematical symbolism. But what you might want to do first is say, okay, no more than 10. So what values are we talking about? We know that X goes from 0 up to 25 because n is equal to 25 in this problem. So no more than 10, well, 11 is no more than 10. We can have 10, right? But we can't have more than 10, no more than 10. So no more than 10 would include 0, and 1 and 2 and 3 all the way up to 10. So in our event, no more than 10 means from 0 to 10. So when we're writing the probability, we're going to write x is less than or equal to 10. I suppose you could say the probability that x is less than 11, because we are in a discrete setting. And so these two look quite different, but they turn out to be the same exact probability. Less than or equal to 10 or less than 11. So either one is going to be equal to, and we're going to use binomial CDF. Same n, same p, but now this last number always corresponds to where we stop. So if we stop at 10, from 0 up to 10, then we're going to have 10 there. And I'm going to punch this in on the calculator again. So we're going to go to the distribution menu. You're going to be using Binomialpdf and Binomial CDF a lot in this section. All right, so we need the 25 and then the 0.45. And since it's CDF, we're accumulating from 0 to this last number, 10. And there it is, 0.384. 38.4% of the time, no more than 10 respondents would say. Okay, and you know what the rest of it is. The morality in the United States is poor. So if you want to continue that. All right, so I want to look for a greater than probability now. Let's see if we have one. There it is, 13, or C, I mean, 36C. 36C says find and interpret the probability. So in each one of these, probability, 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 we're using the probability either binomial CDF or binomial PDF. In this one, more than 16. So we need to translate more than 16. Well, for me, more than 16 is just x is greater than 16. Another way that you can say it is x is greater than or equal to 17, because we're in a discrete setting. You might think this is silly, but if you want to try to figure out PDF, CDF, I would recommend doing this. 21, 22, 23, 24, 25. Right, there they are. And then for each one of these probabilities, circle the values that correspond to the probability. So x greater than 16 or x greater than or equal to 17, you want to add up all these probabilities, the probabilities at each one of these x values. Unfortunately, our binomial CDF function adds up probabilities from 0 to some ending amount. So if you have a greater than probability, here's how we're going to do it. We want to sum up all of these. We don't have a calculator function for that. So what we're going to do instead is we're going to sum up all of these. And the sum of all these is binomial CDF 25.45 and ending at 16. There's the ending value. So the ending value is what goes in that spot right there. And we know that the sum of all the probabilities add up to 1. So if we can sum up all the probabilities here, if we subtract it from 1, we will get the probability of what we want. So this is how we evaluate a greater than probability. We take 1 minus a CDF function. All right, so let me calculate that here. 1 minus, and we're going to go to the distribution menu, CDF, 25.4, and ending at 16. And there it is, 0.017. So all of these would be 0.017. There's only a 1.7% chance that 17 or more people would say that morality in the United States is poor. The less than probabilities are easier, just uses binomial CDF. The greater than probabilities, you have to take 1 minus the binomial CDF. And we will definitely practice this. In a problem like D, it says find and interpret the probability that 13 or 14. Okay, for this one, I think probably what I would do is just do this, 13, and just calculate those two individual probabilities and then add them together. This one would be binomial. Again, it's at a specific value, so I'm going to use PDF. Same N, same P, okay, and then 13. And then add that with binomial PDF, 25.45 and 14. Just add them together. Oops, did a CDF there. I said those are too high. Let's try again. There it is. 13 and 14. Yeah, those are better. So for the 13 one, we have 0.124, and for the 14 one, we have 0.0, we'll call it 87, 0.087. And then add those two together to get the final estimate, 0.211. All right, it doesn't ask us to do it, but other problems will. So what is the expected value? We have N is equal to 25, and we have P is equal to 0.45, which makes Q equal to 0.55. The mean is N times P. There's our formula. It's very quick. 25 times 0.45, and I'm going to type that into my calculator, and we get 11.25. So you should find that when you look at the probabilities here, the one closest to the mean is going to be the highest probability. So something probably 11 is going to be the highest binomial probability here. And the standard deviation, by the way, the expected value over here is the mean. So it's not another calculation. You know, whatever we calculate this for, that's the expected value. And the standard deviation by formula I introduced earlier is the square root of N times P times 1 minus P, or times Q. And I'm going to punch that into the calculator. Square root of 25 times 0.45 times 0.55. And I get 2.48. Okay, again, they didn't ask you to do it on this problem, but if they did, this is what you would find. And so we can have these decimal numbers for means and standard deviations, even if they're not possible X values. Is there anything else here? Yeah, would it be unusual? So remember, when it says, would it be unusual? You still have to calculate a probability, because the only way to determine if it's unusual is if you calculate the probability and find that the probability is less than our standard of 0.05. Would it be unusual to find 20 or more adults who believe the overall state of moral values is poor in the United States? Why? Okay, so why don't you go ahead and use your calculator. I'll give you 30 seconds. This is part E. What is the probability? And it says to find 20 or more. 20 or more. So we convert that to an inequality. 20 or more, not 19, not 18, not anything less than 20. 20 or more means 20 or 21 or 22 or 23 or 24 or 25. Could we stop at 25 because that's our N value? Okay, type it in, type your answer into the chat. I'll give you 30 seconds. We know it's going to be usual just because we've already calculated the probability that X is greater than 17 up here, greater than or equal to 17, and got a number. You know, if it only occurs 1.7% of the time, then it's unusual. And if we went X greater than or equal to 20, we would be excluding the sum of 3 probabilities that already exist. So it's definitely going to be unusual. Question is, what is it? No one's brave enough to put their answer in the chat yet. Anybody else? We have 4 answers that are all the same, all incorrect, but I know that you did some things correctly. Point 1, 2, 3 is what the answer should be. Now, let's see where those of you who are starting to understand this and wrote that answer 0.00007, you're almost there. And here's what you did. 1 minus binomial CDF, 25. The hardest number to determine is that last one. And the last number for a greater than probability is the last X value that you did not include. And since we have greater than or equal to 20, we want to sum up the 20 and the 21 and the 22 and the 23 and the 24 and the 25 X values. The ones we don't want to count up are all these X values that begin at 0 and end at 19. Since we don't want to include any of the probabilities from 0 to 19, 19 is the largest number that we don't want to include, so that's the number that goes here. So it's not always the number that appears in the probability here that you put in this last spot. You really have to do this analysis and say, okay, what is the last for greater than probability? What is the last X value that I'm not including? So for those of you that got the 0.0007 number, you put a 20 here. And so like I said, you had it mostly right.